Hello, in this video we will talk about chemical kinetics from the mechanism's point of view. So previously we talked about rate laws and concentrations of reactants and rates, things like that. And now we talk about the mechanisms behind how a reaction actually happens. And so first we introduce what mechanisms are, and then talk about how you can determine the rate law from the rate determining step in the mechanism. Alright, so let's motivate this here. So if you have NO2, a gas, it reacts with carbon monoxide, great. Now if you looked at this, you might think that the rate law expression would be rate time equals the constant, concentration of NO2, concentration of carbon monoxide, both to the first power. Because they're both in this equation, right? Sure. There's a reason why we warned you against doing this before, is because oftentimes that's not correct. So experimentally for this reaction, the reaction rate is second order in NO2 and doesn't depend on the concentration of carbon monoxide at all. And so the reason why there's a difference here is due to the mechanism of the reaction, how it goes about going from the reactants to the products. It's not something we've had to discuss before, but it's a really complicated thing sometimes, how you go from one place to the other. And so let's define reaction mechanism. So it's a series of elementary reactions which make up an overall chemical reaction. Again, the steps along the road to go from reactants to products. And so for this reaction, here's a possible mechanism. So first we take two NO2 molecules, react them together to form NO3 and NO. And then you take the NO3 and react it with carbon monoxide to make NO2 and CO2. Okay. Now, one thing about a mechanism is it does need to add to the overall reaction. So let's test that. So we just add these two together, and alright, in doing so, you'll notice that there's NO3 present on both reactants and products side, so we can cancel that out. And then, well, there's NO2 on the right, and then two NO2s on the left, so we can cancel out one of them on the left. And then we add this together, and we get the overall reaction. I didn't put the physical states in there, but you can do that. And hey, look, it's the same thing. Great. So that's one of the ways that we can tell that this mechanism is feasible. Does it add to the overall thing, right? Because your steps need to add to the overall process. Okay, now we have a little more to discuss before we can go about talking about rate laws of reactions. And that is what the elementary steps look like. So each one of these pieces of the mechanism is called an elementary reaction, and an elementary reaction, you can maybe define it this way, is that the rate is proportional to the each reactant raised to the power of its molar coefficient. Maybe this will make more sense when I put this up. Right? So you look at this, you have N2O5 as a reactant, the rate is equal to the constant times the concentration of N2O5, first order, because there's no coefficient. Right? The thing you may have been tempted to do before, you can do it now as long as it's an elementary step. And so you know it's an elementary step if either it's a piece of a proposed mechanism, or if we tell you this reaction occurs by a single elementary step. So the little red box here is to remind you that you can't do this all the time. You can only do it for elementary steps or elementary reactions, whatever you want to call them. Now, with elementary reactions, we have three different types, and let's talk about them. So in a unimolecular reaction, it's really just one molecule that starts out and goes and does something. So this molecule doesn't need to collide with any other molecules to make the reaction happen. It just does the reaction. So I drew the little picture here of, maybe one piece turns into two pieces. Great. You can have a bimolecular reaction in which two molecules have to collide in order to make the reaction occur. And so here's an example here. So your molecules collide, react, and either stay together or go on about their business separately, whichever, right? You have two pieces that are reacting in this elementary step, and then your rate is equal to the constant times the concentration of each one of those two pieces to the first order power. Another example here is if you have NO2 gas that reacts to form NO and oxygen. Now here, your two pieces that are colliding in the bimolecular reaction are the same molecule. Great, so you can say the rate is equal to the constant times the concentration of NO2 squared. And now, when we were doing second order kinetics previously, we were doing them all with the assumption that it's one piece that goes to products, because that made the math easy and possible. And so this is an example of a reaction that you could do the kinetics on. Whereas the one on top, we can't do the kinetics rate law calculations on that, like, integrated rate law stuff. But we can plug numbers into this. If you have concentration of NO, a concentration of O3, great. You can plug those numbers in and find the rate. All right, then there's also termolecular reactions, where three pieces are bouncing together or colliding together in order to make the reaction happen. So in this example, they bounce together and then come apart like that. Okay. Now, termolecular reactions are pretty rare because getting three molecules to collide simultaneously with enough energy in order to make the reaction happen, that's pretty unlikely. And then there are no elementary steps with four pieces colliding together because the statistical chance of that happening is pretty much zero. And so we don't know of any reactions that happen that way. So, okay, if you have a termolecular reaction, then again, since it's an elementary step, you can just take the rate equal to the constant times concentration of each of the pieces. Hey, look, we have two I's, so it's I squared, and we have argon. Boom. Now, so those are elementary steps. How do we go from that to figuring out the overall rate law for the reaction? And so what you do is you look at the mechanism, and whichever one of those steps is going the slowest, the rate law for that step is the rate law for the overall reaction. So here's a chemical example. So now we're back to this reaction that we started with and the mechanism we started with. So now that we talked about individual steps, you can do this part. You can say, okay, since there's a 2 right here and there's only one reactant, here's the rate. Great. Or if you were talking about reaction number 2, there's only one of NO3 and one of carbon monoxide, so they both go here. Great, right? Now, whichever one of these is slowest gives the overall rate law for the reaction. It turns out that the first one is the rate limiting step because it's the slower of the two steps. Okay, so then from that we can say that the overall reaction rate law is equal to the rate of step 1, right? And check it out, that matches what we said at the beginning, that this reaction has an overall rate law of rate equals constant NO2 squared and doesn't depend on the concentration of carbon monoxide at all. So great, we've now solved this mystery. Now, one other thing I should name and point out here is pieces that are formed in one step and then reacted away in another step are called intermediates. And so these intermediates really do exist. They just exist for a very short period of time, and experimentally they're very, very hard to see and look at, but they do exist. Okay, hopefully that makes sense. Maybe an analogy will help too, right? You can use the phrase rate limiting step in everyday life. You're trying to leave the house. Your kid can't find one of their shoes. You're all waiting on the kid. The kid is the rate limiting step. Or maybe you're trying to leave the house and your professor is wandering around trying to figure out what the heck to do, and then he's the rate limiting step. Sadly, that happens more often in our house. Okay, something else to say is how these multi-step reactions relate to reaction coordinates. And so I haven't taught you this yet. My intent is that comes in a subsequent video, but I'm going to talk about this here for two reasons. One, if you go back and watch this video before the test, it'll make sense. And two, if you're not in my class and you're watching this video, maybe you already know this. Hi. Okay, so we have these things called reaction coordinates, which describe the process of the reaction from beginning to end. And then there's a lot of pieces in here. Reactants are on the left. We have these activation energies, it's called, to go from this baseline to the transition state, how much energy you have to absorb. Then there's the intermediate. Here's the second transition state, how much energy that requires. And then here's where the products are. And now, if you have a two-step reaction and the first one's the rate-limiting step, what that means is it means that the activation energy for the first step is higher and it takes longer, more energy to make the first part happen. And then once you're there, great, you're done. So this would be an example of if the first step is rate-limiting. Now, if you have a different setup and the second step is the slow step, that means that the activation energy for the second step is higher. And then, you can get over the first step pretty quickly compared to the second step because you need to have collisions with much more energy to make this second step happen. And then once you made it to the top, sweet, you're done. And so this would be an example of the second step being rate limiting. Okay, now if those last 2 slides made no sense to you, don't worry, we'll talk about it in a future video. Now, moving forward, tying up our knowledge of reaction mechanisms. Okay, what are they? There are some of elementary steps, and they have to add to give the overall balanced reaction. Now, the rate limiting step predicts the same overall rate law as what you determine experimentally. Great. And then in the overall rate law, also, we can't have any intermediates, because when you use the rate law and you're not thinking about the mechanism, it'd be really weird if your reaction had a rate law with a thing in it that's not actually in your reaction. I mean, it is produced as part of your reaction mechanism, but it's not a reactant that you can play with the concentration of. So we typically try to get rid of intermediates in the rate law whenever we can. Now, another thing is that reaction mechanisms are very hard to prove conclusively. You can show evidence for a mechanism. Look, it matches the rate law, it matches these other things, this one's getting more and more likely to be true, but maybe there's a mechanism you haven't thought of yet, and maybe that one's actually true. And so it's really hard to conclusively prove a mechanism, but you can provide a bunch of evidence for it and get pretty close. All right, so let's put an example here. So a proposed mechanism for a reaction is this. So write the rate law and write the overall balanced chemical equation for the overall reaction. Feel free to pause the video, give it a shot, and then start the video and I'll give you the answer. All right, so the rate law comes from the slow step, right? So if we look at the step that's labeled slow, it has C4H9Br as its only reactant, and so that means the rate of the overall reaction is just dependent on this one reactant. Okay, now what is the overall reaction? So in order to do that, we're adding, and so we can cancel out this one, and then we can also cancel out this intermediate. Fine. Now that's all you can cancel out, so then you just add it up, and here's the overall reaction, which is first order in C4H9Br, and the rate doesn't depend on the concentration of water at all. Okay, in another example, this reaction here, it has an experimentally determined rate law of first order in carbon dioxide and first order in hydroxide. Now, could this mechanism be correct for this reaction? Well, got to check it out. So the first thing I'm going to do is I'm going to make sure that the steps add to the overall reaction. So here's the steps, and then here's the intermediate, this bicarbonate. You can cancel that out. And now, great, you add the first and second together. They add to the overall reaction on the last slide. Great. Now, the other thing we have to check is, do the rate laws agree? And so for the first elementary step here, your rate law depends on carbon dioxide to the first order and hydroxide to the first order, because you can look at the coefficients here because it's an elementary reaction or an elementary step. Now, if you look at the second step, if this was your rate limiting step, the slow one, then your overall reaction order would depend on the bicarbonate concentration. Let me just add this negative sign here. Oops. And the hydroxide concentration. Does it? No. So then that tells us that the mechanism would predict an overall rate law of first order in carbon dioxide and first order in hydroxide. And hey, this matches what we said at the top. So that means this mechanism could be correct. This doesn't prove that it is correct, but it says that it could be. So hopefully this all made sense. And this is all I have for this video, so see you in class.